Arvind, should we start now? Okay, sure. Hello, everyone. Welcome to SCAM Live Solution. This is Shan from SCAM Marketing Team. As usual, we are happy to has this expert-led and lightning-fast live solution. Today, we are glad to have Arvind here. Arvind is our silver level coach and gold level teacher. Also, he is a very serious, heavy way in competitive programming. He makes the ICPC World Finalist and also ranked number 6 in the North American. We are thrilled to have Arvind here to our live. Let's hand over to Arvind now.
Right. Hey everyone. So I'll first talk about the bronze contest. There are three problems. I guess personally for me, I took the one last month and felt like this one was in general kind of easier, or at least like problems 1 and 3 were probably on the easier end. And then problem 2, yeah, I guess like yeah, I guess problem 2 is like it's kind of a brute force problem, and I'll talk about a bit more about it later. So let me first talk about general strategy when like opening a contest, right? So I have a copy of the problems here. So generally a good strategy is just to like read all the problems in the beginning. Since you never actually know like which one might be the easiest, maybe problem 1 will be the hardest one. And also like looking at the subtasks is generally like pretty useful, right? So in this one, like you know that there's like one test for each different value of n. So in general, it's just pretty useful to look at all the problems in the beginning, and then just like make a plan for what problems you're actually going to do in the contest, right? But with that, I'll start talking about problem 1, right? So I think problem 1 was probably the easiest for many of you. So let me get my annotator. Right. So this problem, it's like you have a keyboard that has 2 letters, M and O. And then like every time you type in O, the letters get flipped, right? And then Bessie has like a favorite moo that's in the input. And then the question's asking if it's possible to find if it's possible to type the favorite moo, right? Yeah. And then there's a lot of different subtasks for this problem. The key observation to make in this problem is that, uh, so just like part of it is about reading the statement a bit carefully, right? And like actually understanding how this works, right? So, uh, like if she types M, then uh, yeah, uh, if she types M, then the basically the letter that's added at the end is M. And then if she types O, then the letter that's added at the end is O, and these get flipped, right? So what this tells us is given the input, like you know that if she typed M last, then the last letter is gonna be M. And then if you know that she typed O last, then the last letter is gonna be O, right? So this actually gives you a lot of information about what's the sequence that Bessie actually typed, right? I guess let's look at the k=1 case where you actually have to construct the answer, right? So if the last letter that's printed out is O, then that means the last letter that's typed has to be O. And then these have to be flipped, right? And then if the last letter that was typed was, so if the word is like this, if the input is like OOM, then that means the last letter Bessie had to have typed had to be an M, right? And then it doesn't flip the later ones, right? So this leads to this kind of algorithm where you can kind of go from right to left because you know what's the rightmost letter that Bessie flipped. And then if it's an M, then you know that the next one has to be an O, right? And then if the string is moo, then you know the last letter that was typed has to be an O, and these get flipped, right? So this technically becomes OM, and then the last letter that has to be typed is M. And then this doesn't get flipped, it's just an O. So the last letter that um, gets typed is an O, right? Yeah. So that's like kind of the idea for this problem. And yeah, so this idea kind of leads to an O of n squared solution, which should be enough for like I guess there's like half of the subtask, like more than half of the subtasks, like roughly half of the subtasks, right? So the algorithm is go from right to left. If you see an M, then just put M, or if you see an O, put O, and then flip everything to the left, right? And then the way to speed this up is you can just like keep a Boolean variable that tells you whether to flip the string, right? So yeah, so Boolean variable, it should tell you whether or not to flip. Yeah, whether or not to flip. To flip, right? And then you just go from right to left. Whenever you see an O, like in the flipped version, then you should flip this Boolean variable. And then whenever it's an M, you should just keep the Boolean variable as it is, right? And then based on this Boolean variable, the the previous character before that is going to be either the flipped version or the not flipped version, depending on what this Boolean is. Yeah. Uh, yeah, I'll just summarize the idea. Any questions? Um, yeah, so the key idea, which leads to like which can lead to like a fairly quick solution, is that yeah, you know what the last character Bessie had to type was, and that motivates going from right to left to construct the sequence. Yeah, and then the answer is always going to be yes. Cool. Yeah, so that's how you do this problem. Yeah. Um, yeah, I think the next problem is probably a bit more interesting. But yeah. Yeah, any questions you can type in the chat. Uh, just wait like a few seconds. Okay, let's move on to problem two. Yeah, yeah, so in this problem, you're considering like a board with n cells, and then you're considering like all the labelings of the cells with M's and O's. And then your score is based on like, so you're given these moves, K moves, and your score is based on how many of them give the sequence MOO, right? Yeah, and then there's two tasks here. One where, yeah, n is pretty small and k is also relatively small, like 10 to the fourth. And then input 6 to 12, you have different varying values of n, like 14, 15, 16, up to 20, right? Um, yeah, and yeah, yeah. So what I'll say about this problem is, yeah, so it kind of reduces to finding like which XY pairs are valid. So Um, yeah, and there's like some work that you need to do to actually find this, right? So yeah, so one important constraint here is that there's at most 20 cells, right? So there's at most 20 cells, and you're gonna label some of them as M, and then you're gonna label some of them as O's, right? And since there's only 20 cells, it's natural to consider like all the 2 to the 20 possible labelings, right? And one way to iterate over the labelings is you can think of each thing as a binary number of length n, right? Yeah, so I'll just write it as a number s. So for example, let's say that cells, like let's say that cells, uh, so let's just zero index these cells. So let's say cells 1, 3, and 4 are m. Then we can just let the first bit equal 1. And then the third bit equal 1, and then the fourth bit equal 1, and then everything else be zeros. So if we decide uh, for cells 1, 3, and 4 to be M, and then the rest are O's, then we can represent it as this binary number, right? Yeah, so basically, then the solution ends up being, right? So just consider all possible labelings of M. There's 2 to the 20 of them. And then for each labeling, you want to find the number of moves, right? Yeah, so let's just fix some set S, and this will be your corresponding labelings of M's and O's, right? And then yeah, and then after you fix X S, then you want to like find all the X. So it's sufficient to find all the X, Y, Z tuples where like uh like the Xth bit is equal to 1, and then the Yth bit is equal to 0, and then the Zth bit is equal to 0, right? So you want to find like all the XYZ pairs where the X bit is equal to 1, and then the Yth bit is equal to 0, and then the Zth bit is equal to 0, right? And then you can pre-calculate in the beginning, like how many of these moves have like the first one equal to X, and then the second one equal to Y, and then the third one equal to Z, right? And then the contribution of this XYZ tuple um, is going to be the frequency in the input of how many like in the input how many times for how many rows X is the first element, Y is the second element, and then Z is the third element, right? Yeah, so one thing that helps is you can just pre-calculate in the beginning, like how many X, Y, Z's are in the input. So you just like, yeah, so we can just make this some array count X, Y, Z. Um, just the number of times X, Y, Z occurs in the input. So you can just pre-calculate this, right? So you can pre-calculate the frequencies of everything in the beginning. And then when you fix S, which is which ones you label equal to M, then this reduces to finding like the all the X, Y, Z, where it's the X one is equal to M, and then Y, Z are equal to O, right? Yeah, so naively, if you implement this, there's n cubed possible, there's n cubed possible, yeah, I'll just use capital N. There's n cubed possible XYZ tuples, and then there's 2 to the n, yeah, and then there's 2 to the n possible values for S, right? So this runs in n cubed times 2 to the n. So n cubed times 2 to the n is actually the intended solution for this problem. But if you naively implement it, it'll probably TLE, like, or at least when I implemented my first versions of this, I think I passed up to test case 19, and then a TLE on the last one. But you can like kind of optimize this a bit, right? Uh, yeah, so I'll talk about a couple of optimizations you can make. Let me just summarize what we did so far, right? So we're just iterating over, or we're doing casework over which ones are equal to M and which ones are equal to O. And then we're iterating over all the tuples, X, Y, Z. And then we're making sure that the X bit is 1, and then the Y bit is 0, and then the Z bit is 0. And then for each X, Y, Z tuple, we're adding the frequency of X, Y, Z in the input, right? So a couple of optimizations we can make is let's look at here, right? So the order of these two things actually doesn't matter, right? So you can just replace it so that instead of 5, 3, 2, it's 5, 2, 3. So we can assume for every X, Y, Z pair, Y is less than Z, right? So this by itself should speed up our solution by yeah, like a factor of 2 if we just only iterate over XYZ where Y is less than Z, right? And then another optimization we can make is when you're looping through XYZ, you don't need a loop until N for all of X and all of Y and all of Z. Just take like the 0 indices and then take the 1 indices, right? Um, yeah, okay. Yeah, I'll just call this, yeah, let's just say S1 are the indices where it's equal to 1. So like S1 can be this vector, and then S2 is all the indices where it's equal to 0, right? So for a fixed S, the number of things you're actually going to iterate over is, so X is going to be part of S1. So it's going to be size of S1, and then Y and Z are going to be in S2. And then we also assume Y is less than Z. So it's going to be sorry, N minus S1. So it's just size of S0. Yeah, I think this was S0. Sorry, it's a bit messy. Yeah, sorry. S1 is like all the indices that are set to 1, and then S0 is all the indices that are set to 0, right? And then X has to be in S1, and then Y and Z have to be in S0, and Y is less than Z. So the number of things we actually iterate over is going to be size of S1 times the size of S0, choose 2. So I just write that as n minus size of S1, choose 2. And if you like test this for a few values, I'll just erase this part. If you like actually look at what this is, this ends up being much smaller than n cubed, right? So if you calculate for a few values, this is less than zero point 0.1 n cubed, and on average, it's going to be much smaller, right? So yeah, so if you iterate over x, y, and z like this, then the time complexity is going to be n cubed times 2 to the n divided by some large enough constant, like that's like larger than 10, right? And this kind of thing should pass. Yeah, any questions? I'll summarize this again. Uh, can you explain how to build S again using the K moves? Oh, are you asking like how to iterate over S? Um, yeah, good question. Yeah. Um, yeah. Yeah, that's important for me to elaborate. Yeah, so S, you can think of it as a bitwise representation of some subset, some set, right? So here cells 1, 3, and 4 are labeled as M. So we can represent it in this bitwise format, right? So you can do this with the for loop, right? So you can do for S equals 0. Um, yeah, I'm just informally writing this for loop, but it's just like s equals C plus plus. You do like s equals 0, s less than or equal to 2 to the n minus 1, s plus plus. Yeah, so I think, yeah, in C plus plus, you can do bit shifts. So this just means 2 to the n minus 1, right? This is how you iterate over the subset S, right? So you can just do a for loop, and then basically you can extract S0 as like indices uh, with 0 bit equal to 0, and then S1 is the indices with bit equal to 1. And then, yeah, and then the way you iterate over x, y, and z is basically you do for x in S1, and then you'll do like a nested for loop. I won't write the whole thing, but just make sure that y is less than z. Otherwise, or maybe it'll pass, but like this gives it a 2x constant factor optimization. I think like constant factors matter a lot in this problem. But basically for all pairs y and z in S0, then yeah, add uh like the count of x, y, z to the answer. Yeah. Yeah, so that's kind of how you should like how you can implement this. Cool. Anything else? Yeah, and I kind of argued that this ends up being like n cubed times 2 to the n divided by some fairly big constant. Yeah, I'll just wait for like 30 seconds in case anyone has any questions. Yeah, so this is a screenshot of when I took the contest. I think I didn't constant optimize my thing this much, so it barely passed. It's like 1944 milliseconds. But yeah, I think if you implement this version, it should be much faster. Yeah, I think mine was like a factor of two too slow when I implemented it. I'll just make another comment. So it's probably too advanced for bronze. Or like, I mean, I'm not saying this problem is too advanced for bronze, but there's like one optimization that you can make. So it's technically possible to solve this in So this time complexity is like n cubed times 2 to the n. It's technically possible to do this in n squared times 2 to the n using a technique called SOS DP. It's called sum of subsets DP. Yeah, I'm not asking you to like learn it, but yeah, this is like a plat level. Like if you want to do this, this is like a plat level topic. But yeah, like uh yeah, there do exist faster solutions um, than n cubed times 2 to that. Yeah, so I think the idea of with the SOS DP is like the first index of your DP is like what you choose for x. And then the second index is the, like where all the zeros are. Yes. So this is like the sum over all pairs y, z in S. Yeah, but yeah, this is not required for bronze. Like to know this, it's not required for bronze or silver, uh, but it might be useful in like gold and platinum. But yeah, just something I noticed. Um, since when I tried the problem, I wasn't sure how to do it faster than n cubed, but yeah, someone told me you can do it in n squared. Um, yeah, okay, let's go to the next problem. Yeah. Um, Yeah, so this problem is purchasing milk, right? Um, yeah. So yeah, you want to like you have like each option is like some power of 2 buckets of milk, and you have to pay like AI moonies. Um, and then you're given an integer x, and you want to find the minimum cost to purchase at least x buckets, right? Yeah. So like some observations you can make, right? So let's say that in the input, like yeah, I'll just write some sample input. Uh, yeah, so maybe this is like, yeah, 4, 5, 6, 7. Uh, yeah, like 50, right? Yeah. So this is like the price for 2 to the 2 to the 0 and 2 to the 1, 2 squared, 2 cubed, and then 2 to the fourth. One observation is that like you never actually need this 50 because it's like much smaller than 7, right? So like instead of getting like this is a 2 to the fourth place, right? Instead of getting a 2 to the fourth bucket for cost 50, it's always better to just get two cubed buckets and the cost will just be 14. It's like 2 times 7, right? So you can take out this 50 and just replace it with 14, right? Yeah, I'll just like visually, I'll try to visualize it. So yeah, so if this one is like very cheap, let's say I'll just denote the height as the price. Um, and then, so this is like AI, and this is AI plus one, right? Basically, it's better to get 2 of these than to get this, right? So I'll just remove this, and then basically you can replace it with this, right? Yeah, so yeah, there's basically this observation. So then you kind of have a condition like AI is should be less than or equal to 2 times AI minus 1, right? Um, yeah. So yeah, uh, we can just so we can kind of go from left to right to pre-process the input to make sure that this condition holds, right? Um, yeah. Let me see if any of the sample cases, yeah. Let me see if any of the sample cases have a nice way of writing this. Yeah. Okay. So let's look at the sample case. Um, yeah. So this says the four costs are 10, 25, 30, and 70. Let's erase this. So I'll just write that here. 10, use black. Okay, 10, 25, 30, and then 70, right? So let's just replace this with 20, right? You can just get 2 buckets of this for a cheaper price. This stays as 30, right? This is better than getting 2 of these. And then let's replace this with 60, right? Okay. Yeah, so we can kind of pre-process this as like this. If you wanted to like visualize it as a for loop, you just do like for I equals 2 up to n. AI is min AI, and then 2 AI minus 1, right? So let's just assume this stuff is pre-processed. So it always holds for every I. AI is less than 2 or less than or equal to 2 times AI minus 1. Just like assume this about the input, right? Right. So basically what this is telling us is that AI is the minimum cost, uh, min cost to get 2 to the I minus 1 buckets, right? Okay. Yeah, so let's just assume this, okay. Yeah, let's just assume this holds for all I, right? AI is up to 2 times AI minus 1, right? Let's go back to the problem, right? Uh, you want to find the minimum cost to purchase at least X buckets of milk, right? So the key thing here is like at least X buckets, right? Yeah, so if it asks for like exactly X buckets, it turns out that's actually something we can do pretty easily, right? So let's write X in binary. So let's just consider the simpler version of the problem where it's asking for the minimum cost to purchase exactly X buckets, right? So that X will be in binary like this, right? And basically, we just need to find the cheapest way to get each power of 2, right? So it's going to be the cost of this plus the cost of this plus the cost of this. So if we are only looking for exactly X buckets, then the answer would just be A of 2. Like A of 1 is the minimum price to get 1 bucket. A of 2 is the minimum price to get 2. So it'll be A of 2 plus A of 4 plus A of 6, right? So in the case where it's exactly X, we've already solved the problem, right? But let's consider we're purchasing, yeah, I'll just write this on the left. So we're purchasing Y buckets where Y is greater than X, right? So if you look at, so when you see something is, uh, uh, sorry, I don't know Hindi, but um, yeah, okay, yeah, okay, uh, yeah. So when, yeah, so yeah, so like this problem is kind of asking about bitwise things with powers of two, and when you want to when you consider like a number is greater than another, like in terms of the bits, what it actually looks like is, let me just draw y over here and then draw x over here. So for some prefix, they'll be equal, right? So for example, this might be 0, 1, 1, 0, 1, and then this might also be 0, 1, 1, 0, 1. And then at some bit, y has to equal 1, and then x has to equal 0. And then this suffix can be anything, and then the suffix can be anything, right? Right. This is something you should always consider when like you're dealing with bitwise things or powers of two, and you're considering like one number is greater than the other, right? So up to some prefix, they're equal. And then after that point, the bigger one is equal to 1, and then the smaller one is equal to 0. And then after that, both of them can be like anything you want, right? One observation we can make is that if y is greater than x, and let's say that they disagree at index, like yeah, at index I, let's say they disagree at index I. If you want to spend as little money as possible, subject to this, so here I wrote it can be anything, but it's always cheaper to just make these all zeros, right? Since you want to spend as little as possible, right? Um, it never helps to like set one of these to 1. You just have to pay more, right? So in the case, so when if y is greater than x, that means that for some bit, the ith bit of x is 0, and then the ith bit of y is equal to 1. Um, right? And then you just find the cost of this, right? Um, yeah, so yeah. So for the case where y is equal to x, you just add the cost of those powers of 2. And the case where y is greater than x, you can do casework on where these bits disagree. And before that, they're all equal. And after that, they're all equal to 0, right? And then, yeah, what you can do is just um, the answer for this case I is going to be the sum of the costs corresponding to these powers of 2, right? Yeah, any questions? I'll just summarize what we did again. Yeah, I can also like rewrite this in a for loop, right? Yeah, so basically we're considering two cases, either y is equal to x, in which case you just add these powers of 2, or y is greater than x, right? And if y is greater than x, basically what that means, there's a bit where there's equal to 1, that is equal to 0. Everything before that are equal. And it never helps us to set any of the later bits to 1, right? So we just make them all zeros, right? Yeah, so yeah. Yeah, so if I were to write this like as a for loop, so for I equals 0 to um uh wait. Yeah, okay, yeah. Yeah, also important thing is that x is like 10 to the 9, right? 0 up to, so you only have to care about like 30 values, right? 30. And then if x bit is 0 and y's bit is 0, 1, sorry, x bit is, sorry, ith bit of x, I'll just write it as xi equals 0 and yi equals 1, then basically calculate the cost of the string. Yeah. And then one detail you need to be careful about is that n is up to 10 to the 5. So you also have to consider like x is like starts with a 1, or like sorry, y starts with a 1, and then it's like 10 to the 5 zeros. But you can just do that like outside of this for loop. So you can have this for loop for I up to 30. And then if I is greater than 30, then you just take the max, you just take the min of the answer you get from here, and then the values of your input that are greater than 30, right? Yeah. So that's how you do this problem. Any questions? Yeah, so I'll just summarize. Yeah, so observation is like, yeah, we can like assume things about the input, right? Because if this one is small, and then this one is like huge, then we can just like replace this with 2 times the small number. So you can just do a forward pass to like make the input a bit nice so that like the ith value gives the true minimum cost of having like exactly 2 to the I buckets. Yeah, and then we just do casework. There's like only 30 relevant cases for how many buckets we should actually buy, because y is greater than equal to x. It's either equal to x, in which case you use these 1 bits to calculate what you need, or it's greater than x, which means it's equal to 1 at some bit where x is equal to 0, and the rest are equal to 0. So you just add these 1 bits. Yeah, and then there's the third case you have to be careful about where, yeah, maybe like an is super tiny and n is like 10 to the 5. Um, yeah, but that's how you do this problem. Yeah. Um, yeah. Uh, yeah, I guess maybe I haven't thought about this too much, but maybe for n equals 10, like you can use some fact that um, like uh, or like the number of buckets is only going to be up to 1,000. But yeah, I haven't really thought about those details too much. Yeah, but that's how you do this contest. Yeah, so yeah, I guess the results should probably come. Generally, they come up in the next few days, maybe in the weekend or something. Yeah, I think this is a good problem to upsolve. Yeah, just to I think bitwise problems come up a lot in um, maybe not just USACO, but just in like competitive programming in general. Yeah, and I think this is also like a pretty educational problem. At least the brute force part, like how to like iterate over subsets and like the bit manipulation parts. Yeah, that's also something that comes up pretty often. Yeah, this problem's a little ad hoc, but yeah. Um, yeah, I think like yeah, if you get like very experienced, like you can probably solve this in a few minutes. Maybe some of you actually did, but yeah. Yeah, that's all I have for this contest. Yeah, right. Yeah, I'll just take any questions for the next few minutes. Thanks.
Arvind, could you stay on the slides cover the bronze problems topic? Because some
Oh, yeah,
YouTube,
sure,
yeah,
of course.
some YouTube they didn't see it. Yeah, thanks.
Okay, yeah. Yeah, yeah, yeah. Yeah. Um, yeah, so I would classify the first problem under ad hoc. Like the biggest part is like making the observation that you go backwards. Yeah. For those of you who haven't like heard of the concept of ad hoc, um, I generally say like ad hoc problems, they don't really fall into any specific topic. They're more about making observations. I think the meaning of the word ad hoc is like the problem is original and there's like not that many problems that are like it, or it's like different every time. Yeah. And then the Muhunt problem was, yeah, this is a brute force problem. Also a good exercise in bit manipulation. Yeah, there's also a good exercise in like constant factor optimization. And a lot of problems, they don't really like require much constant factor optimization, but yeah, it can be good to be good at that kind of stuff. Yeah, and then purchasing milk is more like about bitwise problems and like making, yeah, I guess there was a greedy observation we made in the beginning where like the buckets sizes have to follow like some certain structure, so you can't have like one small followed by one huge one. Yeah, cool. Yeah, this will be on YouTube. Oh, yeah. I think like technically, yeah, technically I think like so there are some places where questions are shared, like in the USACO Discord server. I saw some people sharing it there. Yeah, maybe if you want to like refer to them, you can check there. I think at this level, like at least yeah, the last few times I tried bronze, I think they're mainly ad hoc, like ad hoc and greedy, like you probably won't see dynamic programming, but yeah, I think like a lot of problems like all right, I think this one was on the easier end, but for some problems you have to like you like try a few things and then you fail before you finally get a solution. I guess like my personal like view of this contest was like this was pretty fast to solve, and it's like um I think this kind of had like multiple steps. Yeah, but I think like most problems they're like ad hoc, or I guess this problem was also like bitwise. So uh yeah. Um but in the previous bronze contest, I think they were like pretty ad hoc. Like I think the first problem, like I remember I tried in the first problem I tried using binary search and then it failed. And I had to come up with some other approach and it worked. So I think the first contest this year was more about like trying a bunch of things and failing, and then something works. Yeah. Yeah. So like if you do code forces, I don't know if you all do code forces, but like I I mean maybe not the most accurate, but maybe this difficulty of these problems might be similar to what you find in like Division 2 C, but maybe these bronze problems are more implementation heavy. Like Division 2 B and C, they tend to be very ad hoc also. Yeah.
Thanks, Arvind. We have still have 15 minutes left. Yeah, welcome to ask all bronze level related question here. Yeah, and also silver level we will start at 8 p.m. Pacific time.
Hey, Arvind, thanks for the explanation here. So can I ask some maybe general question if there are no other specific question for this context?
Sure, of course.
Just in terms of actually, my son is sitting right behind me, but so this is his first time trying to like try the test.
Yeah,
Um, I have not been able to actually spend a lot of time with him.
yeah,
Basically, he has taken all the courses up to 301 now. But I think the number of like context questions or mock test questions he has tried or has tried to reflect tend to be limited at this point. I guess I'm just curious, what's the best way to probably speed up the preparation other than, well, it's basically just we need to work on the test questions, mock text questions, reflect and summarize, or any other advice you folks may have actually?
yeah. I think at least for like bronze and silver level, I think it's just good to do more contests, or at least when, or I guess I didn't do competitive programming when I was younger, but like when I learned doing contests, I had an account on Code Forces where I used to do a lot of rated contests. And I think
Uh-huh.
like rating and like competing alongside my peers was like a very good motivator for me. Yeah,
Right, right. I'm
I
just
think,
curious
yeah,
if there are any pattern that has been tested, right? I guess we can one way of doing is kind of try to work on the different kind of questions and then summarize by ourselves. Well, are there anything that has like any summary that's already there saying, these are the typical patterns, something you want to kind of practice beyond just doing the individual questions?
yeah. I mean, I think like, yeah, there are like a lot of patterns I see in a lot of these problems. Like,
Yeah.
I think in this ad hoc problem, just like reading the statement carefully and then trying to look at what things are forced. So I think I mentioned in this problem, like the last, like you gain information about like what's the final character. Um, I think like personally, I feel just like if you do a lot of contests, you do more problems, then you just get faster at recognizing these patterns. That's what I would say.
Right,
Yeah.
right, right. I see. I guess I'm thinking along the lines of, in terms of algorithms, right? There are those classical algorithms we
Yeah.
study. And of course, for those basic algorithms, you can apply them in different ways, combine them in different ways to solve problems.
Right.
And I was just curious, are there for the USACO test, right?
Yeah.
Contest. Are there any, like, in software, there's something called design pattern, right? Something like
Yeah.
that. I was just thinking if there's any pattern of problems that have been summarized already by the community that could provide maybe a little bit shortcut than
Right.
uh, having to work on hundreds of problems ourselves and then summarize and then, or
Right.
maybe that's the only way to go about this.
Yeah, I mean, I'd say like doing a lot of problems is probably the way. But I think one comment I'll make, like, maybe there's less the case in bronze. I think bronze, like, so I think there are like classical algorithms, but they're only tested in higher levels like silver and
Mm,
gold. For
mm,
bronze, it's more like ad hoc, and it's just like you're trying to solve a puzzle, and then you have to try different things, and then until you've cracked this puzzle. But for the more advanced levels, it's also partially about knowing the classical algorithms. But
mhm,
I'll just say generally in USACO, two types of problems I tend to find are like one of them is like more standard. It's either close to a classical algorithm or it's similar to a problem that kind of shows up. And then the
mhm,
other kind of problem is more ad hoc. It's like more
mm,
original, like something that you might have not seen before. And you just need
mhm,
to like try a lot of things before you actually like figure out how to do it.
mhm.
Yeah.
Kind of look at the unique nature of the specific questions and kind of,
Yeah.
uh, I see. Great. Thanks a lot.
Thank you. Thank you.
Everyone. Welcome to SCAM Musical Live Solution. We have some new audience here, so I would like to introduce Arvind once again. Can anyone see my screen? No? Okay. Maybe Arvind, you can share your screen, right? Yeah.
Yeah, sure. Yeah. Okay. Yeah. Hey everyone, I'm Arvind. Yeah, so I'll just make some comments about this year's or this weekend's silver contest. Yeah, so there's three problems. I think for me personally, like I think problem three was the easiest for me. Or it's like more standard. It's like similar to other problems that show up. Problem one was also like kind of pretty doable. And then problem two is like quite implementation heavy. Yeah, I'm not sure how others felt, if they felt similar or different about this. Yeah, but this is how I found the contest. Yeah, and then we'll see more about the problems as I like talk about them. Yeah, so problem one is kind of like a greedy constructive problem. Yeah, and then two is like a very implementation heavy. Yeah, and then three can be done with like very nicely if you use two pointers. Um, yeah, personally, yeah, I think three was a pretty nice problem. Yeah, cool. Um, yeah, let's go into the contest, right? So this is the yeah, so I took the contest this weekend. Yeah. Um, right, this is silver, right? Yeah, so I think general good contest strategy is just to like read all the problems in the beginning, like yeah, and it's like know what the subtasks are. Yeah, uh, like for example, like it seems like you can get most of the points in this problem by doing three subtasks. Yeah, I think yeah, also here the subtasks are pretty generous, like C equals 1, C equals 2. Um, yeah, and then yeah, you can get like roughly half of the points with these subtasks. Yeah, so I think yeah, a good contest strategy is to like just read all the problems. Yeah, so I think when I looked at the contest, I read this and then I thought seemed pretty cursed, so I just moved on to the other ones. Yeah, yeah, I think I did problem three first, actually. Yeah, and then I did one. I think I read two and I kind of had an idea, but yeah, I decided to do one before because it's more clean. Yeah, so let's start with problem one. Yeah, so basically, like, there's a bunch of cows in a line. Uh, yeah, and then Farmer Noge's cows, they tell lies, and then Farmer John's cows, they tell the truth. Um, and then like each of them has to tell like which type of cow is to their left and which type of cow is to their right. And you're given these sequences, but the catch here is that it's like permuted, right? So it's not necessarily the case, if I zoom in, it's not necessarily the case that this cow over here sits to the right of this cow over here, right? They're just like permuted in some weird order, right? But yeah, if you draw things out, you can make like some pretty like some observations that simplify things a lot, right? So let's just like look at the cases, right? So if there's two cows that are standing next to each other, both of these are Farmer John's cows, then the one on the right will say that the one on the left is J, and then the one on the left will say that the one on the right is J, right? So this is the first case if the two cows sitting next to each other are both Farmer John's cows. And then another case is both of these cows are Farmer Noge's cows. Yeah, so there's two N's. And both of them lie, right? So this one will say the one to the left is Farmer John's, and then this one will say the one to the right is Farmer John's, right? So it's kind of like the same pattern you see here and here. And let's just look at the other two cases, right? So Farmer John's cow is on the left, and then Farmer Noge's cow is on the right. Uh, then this cow will tell the truth and say Noge. Sorry, I flipped it. Yeah, this cow will tell the truth and then say Noge is on the right. And then this cow will lie and then say that John is on the left, right? Sorry, no, this cow will lie and say that Noj is on the left, right? And then let's look at the last case where Noj's cow is to the left of John's cow, right? So this cow will lie and say that Noj is to the right, and then this cow it will lie. It will tell the truth and say that Noj is to the left, right? So we can kind of see a pattern here, right? So when they're like when they're the same, when they're equal, then both of these will say John. And then when they're different, sorry, yeah, and then the same here, they're both equal, so they both say John. And in these two cases, the left cow and the right cow are different, right? So the right cow says Noj is on the left, and left cow says Noj is on the right, right? So let's just consider like putting them in the right order, right? Then they'll form this kind of pattern, right? So um, like if these are your cows, whenever a change occurs, like maybe there will be a bunch of J's for some time, and then the next cow will become a Noj, right? And then there will be some Nojes from some time, right? So what these two strings will be if you like rearrange them, I'll just put another color. They'll look like uh uh N over here and then N over here, and then J's here, and then J's over here, right? Right. So more generally, like we can kind of visualize it like this. So there's node over here, there's a node over here. This happens when the cow changes, and then maybe later again, the cow will change. So there'll be a node over here and a node over here. And then maybe the cow will change again later. So there'll be node over here and then node over here, right? And then in between, like they're all going to be Johns, right? And then these are all going to be Johns. This could be possibly empty, possibly empty. Uh, like for example, you can have a bunch of ends here, and then a node here, right? Um, yeah, and then you have a bunch of Johns in the middle, bunch of Johns in the middle, right? Yeah, so these node things could be like next to each other also, right? Yeah, so this is kind of like what the structure looks like. Yeah, and then there's like some, yeah, so you can already like rule out certain cases where the answer is no, right? So like a necessary case condition has to be like the number of nodes on top has to equal the number of nodes on the bottom, right? Otherwise, you can kind of rule it out. Yeah, and another necessary case is uh, if you like consider looping through the cows, right? Um, so just consider like the output is like NJ, right? So the number of times that a change occurs is always going to be even, right? So if we start from N, there's going to be a change when we get to J, and then a change when we get to N, and then change when we get to J. We're always going to get back to N when we cycle, right? So the total number of changes is going to be even, right? So also in this case, like if we start from this J, um, it changes to N over here, and then it changes back to J over here, right? So that like after each change, the characters are going to flip. If you start at J, it'll be from J to NJ, NJ until it finally ends at J, right? So the number of changes should be even. And we already know from here, whenever a change occurs, both of them have to be N, right? So another necessary condition, so I guess some necessary conditions uh, is like number of J on the top has to equal the number of, or sorry, number of N on the top. Yeah, so the number of N on the top has to equal the number of N on the bottom. Yeah, and then another necessary condition is like number of N on the top has to be even because like if you go in a cycle, you're going to get back to where you started from. So the total number of flips will be even. So the number of N on the top is even, right? These are just some necessary conditions, right? And now I'll share the idea for how to actually like rearrange the thing to be in the desired form, right? Yeah, so notice like in the input, you kind of have like four kinds of things, right? So, yeah, so like you kind of have four kinds of things at each index. Either there's like JN, or there's like JJ, or there's NN, or there's NJ, right? Yeah, so one way you can kind of rearrange it to get it to work out is like we kind of want to kind of care like so if there's no n n's, like if there's no n like one directly on top of each other, then we can just do n over here. We can just like place them arbitrarily, like and another n over here, and then another n over here, and we can just put j's in the middle, right? Something like this, right? But like it's also possible for n to be on top of n, so we can't have a case like this. But how you can get around that is just group all the n's together, so it'll look like this. We'll have a block of things where n is always on top of n, right? So this will be our block. And then we know that we're required to have an n over here just because of the structure. Like n has to be the top right, and then n has to be the bottom left whenever it occurs. So this n is forced, and then this n is forced. Let's say this is a j, and let's say this is a j, right? And then the rest of the n's, you can just arrange them like put n and n over here, right? And then put another n and n over here. And you can make all j's, right? Yeah, I'll just put the n's in boxes, right? Um, yeah. Yeah, so another condition that you have to check is that so if you just look at this, yeah, and then the rest of them are equal to j, right? So if you just look at this, like condition you can see is uh yeah, so the count of the things where n is on top of j is the same as the count of the things where j is on top of n, right? Yeah, so this is another necessary condition that you need. But yeah, yeah. Basically, if there is something in the input where n is on top of n in the input, then you can arrange it like this, and then put this n over here, put this n over here, and then keep repeating n, and that works. Yeah, and then the other case is where you never have n on top of n in the input, so you can just do n, and then just put j's over here. So wherever n's occur, you can just do this. Yeah, and you still have this necessary condition where the number of n's on top of j is equal to the number of j on top of n, right? So something like this is, hold up, uh, yeah, this should be nj, sorry, nj, and then you can just like fill the rest of them with j's, right? Yeah. Any questions? I'll summarize this. Yeah, so I think the most important part when you're like doing this problem is, yeah, try to like, yeah, like actually look at what they guess when they're next to each other. Like I think yeah, like basically how I came up with the solution is I had to look at, like when two cows are standing next to each other, what kinds of things will they reply, or will they say, right? And then we can notice that when the two cows are different, they'll say n, um, where it'll correspond to these indices in the input, right? And then when they're different, then they'll both say JJ, right? And then it remains to find a construction, right? And then a construction is just consider all the things where n is on top of n, just put them together, and then this n is forced, this n is forced, and then just keep making these diagonal n's, right? And then if there's none of these vertical ones, then just make a bunch of these diagonal n's, right? Yeah, any questions? Yeah, I actually haven't looked at what are the subtasks for this problem. Oh, I guess like, yeah, C equals 1 means you have to output it. C equals 0 means you don't. Uh, could you move the alternating ones to the end? Oh, like to the end of the string? Um, yeah, I think that can work. Yeah, I think it doesn't matter. It doesn't matter too much like where you place these. Yeah, so if you want, you could have, let me change the color. If you want, you could have like the block of ends over here, and then and then you could just like fill. So these have to be J. You can just like fill these with J's. Yeah, so I don't think this really matters. And then you can put N, and these alternating ones here. Yeah, so something like this can also work. Yeah, I think I was like in an Uber when I was doing this problem. Yeah, and then yeah, I just remember like yeah, I think problem 1 and problem 3 were kind of fun, and then problem 2 was a bit cursed. Okay, any other questions? Okay, let's move on to problem 2. Yeah, I think problem 2 is also kind of a mouthful to read. Yeah, okay. Okay. Yeah. Um, yeah, so there's like this weird rule for like determining contestants, right? So yeah, so like I think the way I like visualized this when I was reading the problem statement was like some kind of table where these are the criteria. So this is like yeah, so I'll just write criteria and then let's just label them 1 to C. And then these are the ranks. Let's label them 1, 2, all the way up to N, right? And then some of these cells they're like filled if there's a person that meets that criteria, right? Something like this. Yeah, and then basically the selection is you take the top F1 students from the first criteria. Um, so I'll just like highlight them in red. Maybe we also highlight this. Um, and then among those that weren't chosen, you take the top F2 students from the second criteria. Yeah, I'll just highlight the taken ones in red. Right? So it's always going to be a prefix of it, whatever, right? Yeah, something like this. And then you take the top F3 students, right? Yeah. So I think like, yeah, one observation to make is, wait, let me just make sure. Okay, yeah. So let's say, let's like fix a person. Let's fix a person I. Let me just draw it to the side. Let's draw another table. Yeah, okay, yeah. So the problem statement is like you're given a permutation of people who are like deleted, and then you want to find like maintain the sum of the ranks when people are deleted, right? Um, yeah. So I think like one observation to make, so if this is a table, this is rank, let's say this rank equal to I, right? And these are all the criteria for the person with rank equal to I, right? So one observation you can make is if this one is selected, right? Then these are never going to be selected, right? Because you'll always pick this criteria, like this prefix is always going to grow more and more, right? So you're always going to pick this criteria over these, right? So you're always going to pick this person for this criteria instead of picking them for this criteria. So if you ever are in the situation where you pick some person of a particular rank for a particular criteria, then you can kind of like remove these, right? So that's kind of going to be our algorithm, right? So we assign people, like we assign ranks to the criteria, and then we keep removing the ones that are below, right? Yeah, so I'll just draw a third copy. I'm drawing a lot of copies. Um, yeah, so this is the rank, and this is the criteria. Um, And then like you can think of these black cells as candidates, and we kind of remove these candidates because this one was selected, right? And then basically like for each criteria, some prefix of the candidates, like some prefix is the ranks, you can consider it to be active. And then some suffix of the ranks, you can consider it to be inactive, right? Yeah, so you can like kind of visualize this for all the rows. Yeah. Yeah, maybe it'll be something like this. Yeah. And then I'll just like draw this to the right because we know that like if something is active here, then we already like ruled out the inactive ones here, right? So you can kind of visualize like each row or each criterion, like some prefix of the candidates are active, and then some prefix of the candidates, suffix of the candidates are inactive, right? So you can kind of like initialize this and have a sum. And then when you remove the ith person, let's say we remove the ith person. So this person I, uh, yeah, let's just say there's also like some active ones here, whatever. Um, yeah. So basically when we remove the ith person, let's say the ith person is active for the first criterion, then we can kind of just like remove this and then we extend this forward, right? Yeah. And yeah, so we're going to remove everything for the ith criterion, and then we're going to extend this forward. And when we extend this forward, basically like if there's anything below, since this is active, and since we already argued earlier, if something is active over here and the things below are inactive, then you can kind of delete them, right? Um, and yeah, and maybe it's also possible that something here was already active earlier. And since this active has been transferred to here, then we have to like delete this. And then maybe now this one will become active, right? So it's going to create some kind of chain reaction. Like when we extend, like when we remove the ith person and we extend it, it's going to create like some kind of chain reaction, right? Yeah, so that's like the high level for how you can like think of this problem. Yeah, so I think the data structures I used is like for each row, just like maintain a set of actives. So active just means it's like it's been invited to the contest, right? And we know it forms a prefix and then a set of inactives for that criteria. So this is like a set of all the ranks. And then for each column, we just store like the set of candidate criteria, right? Yeah. So this is how you do that problem. Any questions? Yeah, my implementation's a bit chopped, but I might also show that. Yeah, this problem was pretty cursed. Yeah, and I think, yeah, there are like some details in like the actual implementation, right? Um, yeah, so you need to like, uh, yeah, so when you're removing the ith person, like it's gonna be active in some criterion. So you need to like update, yeah, like if you remove something where it's active, then you need to like update that criterion and then also like remove the things below that active thing. And it's going to create a chain reaction. Yeah. Yeah, I'll share my implementation. Uh, yeah. If I still have it. Yeah, I should still have it. Okay, let me open it up. Okay. Um, okay, let me just give me a second. So this was problem 2. Yeah. Okay. Yeah. Yeah, hopefully this implementation might give like a slightly better idea of how this works. Uh, okay, let me share. Yeah. Yeah, so basically I have 3 vectors of sets I can just draw to the side. Yeah. So like this has length n and then this has length c. And basically, yeah, I store a set of the actives for every column. So these are the actives for every column, and then these are the inactives for every column, right? Yeah. And then I also store for each rank, like which candidates I should consider, right? So you imagine I have like these vertical things, right? Yeah. And then there's just like pre-processing the input. Yeah, I just put these things into functions just so that it's like a bit cleaner, right? Yeah. So basically, yeah, just like we can think of this as a black box now, first, but these are the people you remove. And then basically like we iterate over all the candidates for that particular rank. Um, yeah, and then yeah, so I also maintain some set that tells like which criterion I should actually update. Yeah, so if this criterion is like an active person, then we also need to update that criterion because if we remove someone who's active, like let's say we remove this guy, sorry, my pen. Yeah, so let's say we remove this guy, then that means we have to extend this active thing, right? Um, yeah. Um, and then otherwise, like we don't really have to like if we remove someone who's inactive, then we don't really need to change anything, right? Yeah. And then I have this function called make changes. Basically, like to update is the criteria I need to update. So yeah, basically this is kind of simulates the chain reaction, right? So to update, like we consider the topmost criteria that we actually need to update. Um, yeah, and then like basically in the current criterion, we just like keep extending this active segment. Um, and like yeah, we just keep extending this active segment, like replace some inactive things. And when we make this active, it's gonna create a chain reaction below, right? Yeah, so basically, yeah, you can loop over things below, and then you can simulate the chain reaction, right? So if the thing below was already active, then you need to update like this active row also. If it's not active, then you don't have to update that row. Yeah. But that's the idea for this problem. Any questions? Yeah, so I think the idea, like the observations are kind of simple. Like I guess the main observation is like if someone uh yeah, if someone is active, then you like disregard the ones that are below. I think the hardest part of this problem is like yeah, actually spending time to think about the actual details of how to implement. Yeah. I think yeah, this probably took was the most time consuming part of the contest for me. Okay, let me change my screen share back. Yeah, I did try the gold contest, and I think that also had like some really yeah, cursed implementation. Yeah, I don't think I've looked at the subtasks. Or I think I did, but yeah, so I think yeah, there are some subtasks which are kind of free. Like this is where there's one criterion, so you can just simulate with a set. Yeah, and then this is where criteria equal to 2. I guess it might be slightly easier to implement because like there's not really a chain reaction. There's only like 2 criteria we actually care about. Yeah. And probably this one is brute force. So I think yeah, if you don't like full solve this problem, you can probably get like most of the points. Yeah. Um, yeah. So I think like yeah, full solving 1 and then full solving 3 and then partial on 2 should also be enough to pass. Okay, so I'll talk about problem 3. Yeah, problem 3 is kind of fun. Um, yeah, yeah. So in this problem, yeah, like he has an index J, and then he has AJ written on it, and then basically he's allowed to cyclically shift the elements by 1, and then write down the value. Um, then he wants to find the minimum number of operations. so that the total number of distinct integers is equal to the distinct integers in the array, right? And you need to output that for every starting index, right? So I think like, yeah, one thing to like, it's a bit weird to think about cyclically shifting things. But you can like you don't have to think of the array as circular. You can just think of it as a linear array if you make like multiple copies of it, right? So I'll just draw for this example, 1, 2, 3, 1, 3, 4, right? So let's just make multiple copies, 1, 2, 3, 1, 3, 4. And then 1, 2, 3, 1, 3, 4. And then 1, 2, 3, 1, 3, 4, right? And then this problem reduces to being like for each index over here, you want to find like you can either go to the left or to the right, and you want to find the minimum number of moves you have to make such that you see all the distinct elements, right? Yeah. Yeah. So I think one thing that like you can kind of see like one thing that can be noticed is like if you fix a left endpoint and you decide to only go right until you see all the distinct elements, the places where you see the distinct elements is something you can find via two pointers, right? So I'll just demonstrate, right? Let's start over here, right? So you have to go all the way here to see all the distinct elements, right? So you can do two pointers where you maintain like a map of the frequencies, and then you just like erase from your map if the frequency is ever 0, right? So if this is your left endpoint, then you can iterate all the way here. And this is the first time the number of distinct elements will be 4. And then you just increment this, and then the right endpoint still stays the same, right? And then I'll use another color. You increment this, the 2 goes away now, right? So you have to like keep moving the right endpoint until the number of distinct elements is back to 4, right? Yeah, so basically you can do two pointers like to find for each index how many times I need to go right before I see all the distinct elements, right? And then you can also do two pointers from the right to see from the right how many spaces left I need to go to see all the distinct elements, right? Yeah, so like for special cases, maybe like the strategy is for Farmer John to keep cyclically shifting right or keep cyclically shifting left, right? So yeah, we can just like pre-compute. So um, yeah, so this I mean I'm not saying the solution yet, but these are just like helpful things to observe, right? Um, like if Farmer John decides to go like keep going left or keep going right, yeah, uh, you can calculate this using two pointers in a map. So number of steps left from I to see everything. And then right I, we can define it to be number of steps right from I. Right. Yeah. So, okay, so let's go back to the original problem, right? So it's asking for each I, how many steps do you need to take to see everything, right? So let's consider what like the things we see actually looks like. So let's say this is index I, right? So we're gonna see, of course, we're gonna see what's at index I, and then we might also see things to the right of it, and then we might also see things to the left of it, right? So maybe in our path, we end up visiting these indices, right? And given an interval, the shortest way to like actually visit it is either you go to the right side and then you go all the way to the left, or you go to the left side and then you go all the way to the right, right? Okay, so let me just draw it again below. So let's say this is index I. This is index I, and there are two kinds of paths that you might make. One kind of path first goes to the left and then goes to the right. So this is like case 1. And then the second kind of path goes to the right and then goes to the left, right? This is case 2, right? Let's focus on case 1, right? Yeah, so let me repeat what we just did, or like how we're viewing this problem, right? Or I guess like one thing we observed earlier is you can use 2 pointers to see like if you only went left, how many moves you need to make, and then if you only went right, how many moves you need to make. And otherwise, there's 2 kinds of like ways you'll move, right? Since when you move, you're going to visit an interval. Either you go to the left and then you go to the right a bunch, or you go to the right and then you go left, right? So let's consider case 1, right? So I'll just draw it again here. So let's like focus on case 1. We're at index I, and then we go to the left, and then we go to the right, right? And like technically when we go to the left, the amount we go to the right, we only need to go enough to see all the distinct elements, right? So the length of this, so if this is equal to j, let's say we go left from I to j, the length is equal to right of j, right? So technically for each index I, we want to maximize or minimize over j less than I of the length to go to I from I to j plus the length to go right from j. So it's going to be I minus j, sorry, I minus j plus right j, right? Let's like rewrite this a tiny bit. So we can pull the I out. So it's going to be, yeah, so I plus min over j less than I of right j minus j, right? Right? And there's something special about this. This is just a prefix min, right? So technically this is a prefix, like assuming we already calculated left and right, the answer just like this index, the answer for this index is just the index plus a prefix min of right j plus minus j, right? Uh, yeah, so we already know how to calculate left and right. You just do that with 2 pointers, and then you just do a prefix min of this value over here. So you consider right j minus j for every index, and then you can just pre-compute the prefix min. So for this case where you start going left and go right, the answer is the index plus a prefix min of right j minus j, right? And I think, yeah, you can also argue similarly for the other case. If you're at I, and then you go to the right and then back, this is going to be min over j greater than I of j minus I plus left j. So this is going to be like negative I plus min j greater than I, j plus left j, right? Yeah, so this thing over here is a suffix min. Sorry, not everything, just this part, suffix min. Yeah. Yeah, so this problem ends up being like 2 pointers and prefix, suffix, min. Any questions? Yeah, I think when I originally tried this problem, I kind of like I came up with the wrong solution because I assumed like only the left eye would matter, and like maybe you just go from I to here and then here. But yeah, there are some cases where you have to start going right and then go left. Yeah. Or I think my original idea was like for all these intervals in your 2 pointers, consider the smallest one that contains I, and then calculate for that. But that doesn't quite work. Yeah, but this thing works, right? You can provably like there will be some interval that you visit, and then there's two ways you can visit the whole interval. Either you start right and go left, or you start left and go right, right? And then if you consider each case, it simplifies quite nicely, right? So if you start left and then go right, yeah, so you can write it as some kind of suffix min, right? Yeah. But yeah, I think like to solve this problem, it's like, yeah, yeah, I think it's pretty helpful to like know that these are things you can compute. Like given a position, where's the rightmost place I could go, so that there's that many distinct elements. And so you can use two pointers to the map. So I guess this kind of thing comes up a lot in problems. Yeah, but any questions about this problem? Okay. Yeah, I'll take any questions you'll have. Yeah. Any general questions about the contest or any tips and tricks, anything. But yeah, in case yeah, anyone didn't see, yeah, or I'll just like recap. Yeah, so the first problem was yeah, kind of a constructive problem. Yeah, I guess more constructive than greedy. Um, yeah, uh, or like you had to like understand the structure of uh like like whether like how like when two cows are the same or different, how that changes things. Yeah, and then this one was just like you make one observation and then you have to like think very carefully about how to implement it. Yeah, and this one was a nice problem that you can do with two pointers and prefix uh max/min. Yeah, yeah, thanks. Yeah, I'll take any questions.
Yes, thanks, Arvind. Just I mentioned before, Arvind is our silver level coach. So welcome to take any silver level question to Arvind. Because SCAM not only focus on the algorithm teaching, but also coaching. We do the customized coaching to every student. Yeah.
Yeah, I think one other comment I'll make is like, yeah, I think a lot of silver problems, they're actually like pretty similar to problems you'll see on Code Forces contests. At least the like greedy and ad hoc problems. Like probably like problem two, I don't think I would find this in a Code Forces contest. It's probably like too implementation heavy. But I think the style of the problems for problem one, where you have to make that construction, and then problem two, where you reduce something to uh like two pointers, prefix, suffix, maximum. These are also like pretty fair game for Code Forces contest. So I think like if you do Code Forces contest, that can also like give you very good practice for this kind of stuff. Yeah, I think yeah, I actually started doing contests in college. I never did USACO, but yeah, when I used to do contest, I think like doing Code Forces and and the rating was a motivator. And I also had like other friends who did these contests. Oh, sorry, I didn't read the chat. Oh, okay. yeah, I guess you guys have another chance in a few weeks. It's like, yeah.
Yes, for any student who has the skiwi, SCAM offers the 4-day camp from the bronze to platinum level. Welcome to contact us to get more information. If you are current SCAM student, welcome to ask your class coordinator to get the information. Okay, time is up, and thanks Arvind very much because he's in the Eastern time. Okay, and let's wait, look forward the next SCAM live solution. Good night, everyone.
Okay,
Thanks.
thanks.
I will end up the live.
Right, bye.
Bye.